We're just going to pick up where we left off, and then we have a lab today. It's just an activity lab based on light, but we will have to refresh the memory of how to take light. So yesterday we left off talking about relationships between what two variables regarding light? Wavelength and frequency. And all the waves that we spoke of yesterday, they all travel at what speed? The speed of light, which is 3 times 10 to the 8th meters per second, right? We all have units involved here. All right, so I mentioned that there were some relationships, but I just want to call them out specifically so you know that they are directly or indirectly related. Before I move on, what does it mean for something to have a direct relationship, CJ? Changes the same way or opposite ways? The same way. So if something goes up, it means the other one goes up. That's what a direct relationship means. So STs, what do you think an indirect relationship means?
Opposite.
Right, they move the opposite. So if one goes up, one goes down, or one goes down, one goes up. Okay? So between wavelength and frequency, what's their relationship? Say again?
Indirect.
Explain.
Like whenever your wavelength goes up, your frequency goes down.
Okay. So long wavelength is a fast or slow wave?
Slower.
So a slow wave, okay? This is really off again. I don't know if you guys noticed that. But a long wave is a slow wave. So increase the wavelength is going to decrease the frequency. That's what that means, quantitatively and qualitatively. All right, wavelength and energy. Can I get somebody to verbalize that for me? Jacob, what you got?
The higher the energy, it's direct. The higher the energy, the higher the frequency.
So, sorry, we're on wavelength. We'll get to frequency in a second. So go right back and revise that.
The higher the wavelength, the lower the energy.
Okay, so the long waves are really slow, right? They're long and slow. And so if they're moving really slow, they have low energy. So long wavelength means lower energy. So this is a long wave. Increase the wavelength will decrease the energy. It's not my writing, guys. It's the board. I'll fix it shortly. So that's an indirect relationship. As one thing goes up, the other's going down. Bryce, what you got for the last one?
Direct.
Okay, can you explain, please?
The more energy it has, the more faster it's going to go.
Okay. So fast waves have high energy. That's what you're kind of saying. And then that means fast waves mean that they have a high frequency. And if they have a high frequency, they have high energy. So that is a direct relationship. Good. All right, so we learned the equation that relates the first two variables. Yesterday, we're going to learn the equation that relates energy and frequency today. So I didn't do them 2 in 1 day, so you can kind of slowly digest. And I don't know if I've mentioned this to this class. Your brain likes to see things approximately 7 times before it really has full understanding, full access to information, quick. So if you see something 7 times, I'm calling that as like the best I can do for you. Okay, now I'm going to try to shoot for 7 times, but really it's a combination. So for example, for light stuff like calculations, 2 days of looking at it through notes, you did your POGL worksheet, we have a lab, we have another lab. Okay, so I got you 5 times just in class. Okay, that means on you look back over your notes 1 time, you do a problem set, or get some tutoring on something, that's 7 times. So the theory is that your brain doesn't understand or really let things click until it sees it at least 7 times. That's an average. Some of you guys look at it once, you got it. Some of you look at it 15 times, and you got it. That's an average. Okay? So that's why we do things not so repetitively, but you look at them in different ways throughout the week. All right, so this, I'm not sure I printed. See, did I print this? Okay. So you have a relationship between light and energy. And so this was a study conducted by probably like 17 different scientists. They did some collaborations, but Planck, right here, this guy Planck, it might be CK. I tend to sometimes miss that. I think it's a C. He was the one that actually came up with a constant, which is called the H, or the Planck's constant, that is going to be what we correlate between energy and like an intensity version of light. So we studied hot glowing solids because glowing solids emit light, right? We've all seen like a hot iron ring, like they brand horses and stuff with. What color is it? Really like intense yellow or orange or red, right? So those different colors indicate how hot the iron is. So hot glowing solids tell you how hot something is, which means how much energy it has, and it's all correlated to how it's glowing. So we know that there's a relationship, it's just what is a relationship? So he did relate the hot glowing solids to energy, which he then related to velocity. Well, velocity is not the term we necessarily use, but it's a V. So what unit or what term do we use for velocity? Frequency, right? So we're talking about frequency or how fast a wave is moving. So your equation that you should now know is the relationship between energy and frequency. And this is that equation. So E is energy. What unit should energy be recorded as? Joules, right? We did learn that last unit. And then Planck's constant has joules and seconds in it. Okay? It's not joules per second, it's joules times seconds. So it's like JS, joules times seconds. So this is a constant that you'll accidentally memorize because you'll use it a lot. 6.626 times 10 to the negative 34th. Is that a high or low number? Low, okay, because it's negative 34th. And then so what should V be recorded as? Not seconds. Close. Per second, right? Remember we talked about this yesterday. It's seconds to the negative 1 or 1 per second because frequency is a number of times it passes per time. So like waves per time. So how do all these units kind of come together to make J, to make joules? E is equal to, what's the H's units? Joules seconds, right? Joules times seconds. And then what's the Planck's, what's the frequencies units? Per second, like 1 over second. Okay, so what happens with those seconds? They cancel, leaving us with what? Joules. And that's the energy unit of joules. Okay? So those units should always guide you to are you appropriately plugging in information, or are you calculating correctly, because they will cancel. So alongside, now we call this the modern model because we're approaching what like we currently believe the atom looks like and how the electrons behave. So we've gone through all this history, but we're getting to the end here, okay? So Einstein was relevant in terms of Planck's discoveries, but we don't necessarily calculate with his equation in chemistry, we do in physics, but there is a relationship between these two energies, and we spoke of this in the law of conservation of matter, because we talked about how matter contains energy, and there's a particle wave duality with that. So there is a relationship between the energy and mass, and then the mass that's created, well, I say created, the mass that's exchanged when energy production is there. That's like nuclear decay. Okay, so what we want to do now is actually calculate both of these. Can you guys do question 1? Yay or nay?
Yes.
Yes, go. This is what we started with yesterday. It's a quick review of what you can do. You can probably watch the video. I'll pull it up on the site. Just make sure you pull it up from yesterday. So look back at your notes from yesterday so you have an idea is that you can understand the information you're taking down. If your notes are crappy, you want to take better notes so you actually can understand what you're talking about here. I'm just going to ask you to show your work while I fix the board. I copied this for you, right? Is this on your paper? Good, thank you. This is on your paper. Who saw nanometers and said, I must convert? Good, I got a lot of hands up. So that is the one point of contention because you're just normally plugging stuff into the algebraic expression, but nanometers and meters don't play well. So I give you more than enough work to show you where we're heading. You start off with writing down all your given information, which is going to be clear now because you know your speed of light, you know your nanometers, and you know the question is velocity, aka frequency. I like to rearrange my equation first so I understand how we're plugging it in because this will mimic how I put in my calculator. So I divided by wavelength on both sides. Because we're in nanometers, we had to go to meters first. So this is just dimensional analysis. You thinking about how nanometers and meters related based on how King Henry died. So there's 10 to the 9th nanometers in 1 meter. That gave you 6.33 times 10 to the negative 7th meters. Give me a thumbs up if you've made it that far. That's probably one of your very first steps, so I anticipate you're there. After you then have rearranged your equation, and you say, okay, C, 3.00 times 10 to the 8th meters per second, divided by lambda, wavelength, 6.33 times 10 to negative 7th meters. What units cancel? Meters, and that leaves us with what units? Per second, or hertz, or seconds to the negative 1. They all mean the same thing, right? What did you get when you calculated? 4.7. 14th. Okay, so who did get 10 to the 14th? Just give me a thumbs up. All right, if we didn't, it's probably because, just saying, it's probably because we didn't tell the calculator appropriately what we need to do. Remember, you have to parentheses and then completely divide by parentheses the whole denominator because your calculator is not smart enough to understand that you want those two things separate. So, and then this will be seconds to the negative 1, or hertz, or per second. All right, so this is our frequency. Okay, not that frequency. All right, so I'm going to move along with this same question. I'm not going down to the second one yet. I want you to now calculate the energy of this wave you just found. The energy of this wave, this frequency you just found. So the energy of this helium neon laser. Bailey, what equation are you thinking of here? E equals H times frequency. Do you have the energy for this question? Not yet. Do you have the frequency for this question?
Yeah.
Yes, you have the H value.
H is 6.6.
Units?
Joules per second.
Joules,
Per second. Yeah, per second.
not per second. Joules
Times
times second. So I'm just going to say joule seconds. That's how you can say that easier. Or if you want to say joules times second, that's fine. So this is H. This is Planck's constant, 6.626 times 10 to the negative 34th joule seconds. And then I'm multiplying that by what, Kendall? 4.74 times 10 to the 14th. And I'm going to put that not as seconds to the negative 1, just so we can really clearly see what's going on. I'm going to put it as it actually has the denominator. So I'm putting that over seconds because that's what that really means. So now it should be really clear what unit is on top and bottom. Seconds, yes, we have seconds here and we have seconds here. So what am I doing with these 2 seconds? Canceling them because energy doesn't have anything to do with seconds, right? What is energy? Joules. So when you calculate, what do you get for your joules? 10 to the negative 19th joules. Alrighty. So now you've connected all those qualitative reasonings. We were like, oh, long wavelength, slow wave, low energy. Short wavelength, moves really fast, high energy. So we kept saying that. We kind of knew some of those relationships. That this is the quantitative way to approach it. This is the calculation basis. So understanding the 2 equations, their units, and how they play together is really what our goal was for today. Okay? So let's do one more, just to verify you're good. I want you guys to do that FM radio one, because I want you to think about what megahertz is, mega, on the front. And I don't want you to solve for wavelength. I want, actually, no, yes, I want you to solve for both. I want you to solve for wavelength and the energy of this wave. You guys remember where M is on the metric system line? Yes or no?
Yeah.
Yes. It's 3 to the left of kilo, not base, kilo. Ooh, I see a lot of naked numbers. What do you tell me things? some of you guys maybe have already finished. Some of you guys are processing still. I see some of you guys going back and fixing megahertz. So if you need the help, I'm going to run through this one with you. Megahertz is a very large unit, so we want to go back to base because that's what all of our equations are working with, their base. Hertz is just another base unit, but we're not too concerned with the hertz part of it. We'll convert that to per seconds in just a moment. So there are 10 to the 6 hertz per base. Per megahertz, there is 10 to the 6 base units of hertz because there are 6 zeros between base and mega. So that got us a pretty large velocity or frequency, 9.85 times 10 to the 7th hertz, which is going to be moving pretty fast, but not as fast as some of our other things, which have been like to the 14. So this is a radio wave. Is it long or short? Really long, right? And so it's much longer than like a gamma ray. So is it moving fast or slow? Slow. So the frequency should be low, right? So that's much lower than some of our other frequencies. Once you have your frequency and you're solving for wavelength, you're using the speed of light equation, when you divide by your frequency, what unit cancels? Per second, right? So the slash seconds, so we're going to cancel both per seconds here, leaving us with meters. How long is that? Like, you can visualize that, right? So like 2 desks here, what, like 1.5 meters probably? So put 4 desks together and that's the length of this FM radio wave. It's pretty long actually. So once we get our wavelength, do we use this in the next equation? No, this was a standalone question, but the energy is related to the frequency. So we run back up to frequency, and we're going to plug it into the energy equation. E is equal to hv, h is a constant, v was what we calculated at the very beginning of this. In seconds, or utilizing the seconds here, we're going to cancel out seconds and per seconds, and then leave us with joules, which should be our energy. This comparatively is lower in energy compared to the one we just calculated because radio waves are pretty slow, so they're going to have low energy. All right, give me double thumbs up if you get your speed of light equation and then the energy equation. It just takes some looking back over and practice. It's algebra. If you understand what variables are given, you're solving for one. Okay, so I'm not doing any more right now, but I can do some more tomorrow. We good? All right, so pull back out problem set 4. Let's check over a couple of those fast, and then we're going to go back to our lab. I hid it away from myself. There it is. Okay. I like the true false because 1, they make you think, and 2, they're good to make you get your concepts underway. So it's beneficial to check it in a separate colored pen so you know what to go back and check over or review. Okay, so let's start with that. 1, not true. 2, sometimes true. 3, always. 4, never. 5, always. 6, never. 7, always. 8, never. 9, always. 10, always. 11, always. 12, never. 13, always. 14, always. 15, never. And then for the matching, I think it'll be easy for me to read this off for you. 1 should be T, as in toy. 2, S. 3, R. 4, P. 5, N. 6, O. 7, Q. 8, I. 9, K. 10, M. 11, J. Just the definition on that one. 12, L. 13, D, as in dog. 14, B, as in boy. 15, H. 16, C, as in cat. 17, F. 18, E, as in elephant. 19, A. 20, G. Those are just definitions, and that reading guide 4 had some of those on there for you to double check. All right, I'm gonna leave this here for a second so you can check your math, but you did have opportunity to check over your answers on getting that because you had the 3 answers in the bottom. So you converted decimals or percents to decimals, multiplied and added. Check. Chlorines, they gave you specific masses here, not just the dash math. They gave you specifics. So you got the approximate chlorine's atomic mass of 35.45. Silicon, you were given percents and masses, percents and masses, percents and masses. So 3 of the same exact questions essentially, just using different compounds. And 4, and I don't have 5 up here for some reason. 4. We have a concept right now. Hold on. I didn't put it first. Really hard. Oh, I wrote 5 for 4 here. So the halogen in period 5, where are the halogens at, guys? I'm over here now. Where are the halogens? Group. Halogens are group what? 7, and then group 5. Let me grab a laser here. Because this is for for a modified problem set, so let's do this real fast together. So halogens are group 7, where's period 5? 1, 2, 3, 4, 5. So rubidium period, all the way over, what is it? Iodine, and then that's going to be considered a nonmetal. Group 3B, period 5, so group 3, 1, 2, 3, that's boron group. Period 5, down here with rubidium, so it's indium. Cool one, that's used in a lot of electronics. And then alkaline earth metal in period 3, where are the alkaline earth metals? Second group, okay, three, okay. So alkaline earth metals are this P group here, and in the third period 1, 2, 3, so that would be magnesium. And then lost. Oh, I'm sorry guys, I did 3A. Go back to B for me real fast. Group 3B, period 5. I was looking at the lower one. 3B, where is 3B? They're in the transition metals, right? So the B elements are the transition metals in the middle, all this blue stuff. So we go group 1, group 2, group 3. So this is group 3, period 5, who would it be? Yttrium. Why? It's a little town in Nova Scotia. It's a little town, and that they discovered yttrium there, so that's why they named it that. That's why. What was the fourth one? Group 3A and period 2. So where's group 3A? Who's it begin with? Boron, and then period 3, which one would that be? I mean, sorry. Period 2, who would that be? Boron to the top of the line. So yeah, just make sure you count your periods. Totally flushed out here. Okay. All right, let's talk lab stuff. Okay, so pull out a piece of paper for me. All right, so we've all seen this Pink Floyd t-shirt. The white light is not made of white light. It's a bunch of colors. Okay, so I'm going to just pass up 4 of these for now. Alright, so you guys, all you're going to do is hold up. This is a spectroscope. Spectroscope, special fancy piece of equipment. All it has is diffraction grating in the end of it, which is a prism. The prism helps to like separate wavelengths of light, so that's what this is going to do for us. So these lovely volunteers, and then the rest of us in a second in the lab, we're going to take the eyepiece, and we're going to point this little slit. It's going to be on our right hand side. And we're going to just point the little tiny slit up at a light source. And then you guys tell us what you see. Ooh, ah. Okay, tell me what you see. Bunch of colors. Bunch of colors. So you see, like, not white light. Not white light. Okay, so when we look at the light, it's white light. When we look through the diffraction grating, we see a rainbow of colors. Okay, put it down for me. Resist the urge for a minute, because the rest of us are going to get this in the lab in a second. All right, so what we read on there's these little teeny numbers, and the numbers are supposed to give us indication of wavelength. Well, it's not going to be like, hey, I'm 7.0 times 10 to the negative 7 meters, because these are really tiny devices. They just don't have that much space to give us that much detail. So instead, they give us information in angstroms. A with the halo, okay, angstrom. So an angstrom is related to wavelength in this way. Little bitty, teeny tiny angstroms are equal to 1 times 10 to the negative, or 1 times 10 to the negative 10 meters. That's super tiny, right? Yes? You also, instead of doing it that way, I prefer to keep like exponents non-negative. It's just easier to work with. So a lot of times I like to say this conversion factor, 1 meter, one big huge meter, has 10 to the 10th angstroms in it. So are angstroms big or little? They're very, very little. They're very small. Okay? So that's just me telling you how to read the spectroscope, because it's just in a slightly modified unit of meter, just because of the way that this is going to be describing information to us. What are these little things down here called again? Don't get crazy. It's just exactly what you see. Okay? Those are lines, and they're not dull in color. They're bright. Okay?
Spectrum.
Bright line spectrum. Okay, bright line spectrum. There we go. I told you chemists are not creative in how they name things. Those are all bright line spectrum. Oh my gosh, they're all different. What do we call those for the atoms? Atomic fingerprints, because supposedly they are all different. Okay, so we have some samples. We have hydrogen, helium, neon, iodine, and a couple of others that you guys will see today. All right, so this is just a fun fact. This is important actually because they look at stars with different forms of spectroscopes, but they can see what's present in certain cellular matter based on the atomic fingerprints they relay. So they can tell if a star cluster is made up of mostly hydrogen or helium, or if there's other heavy metals that are starting to form there. So it's all gaseous there. So that's kind of cool. Okay, so I'm going to explain this when we get back here. Now, I only have so many spectroscopes. Most of you guys will get one, but you'll have to share a little bit. And I have the labs just because I've modified some here, so I'll pass this back to you. So just turn around for me first. You guys have a piece of paper off to the side, right? Okay. Call it spectroscope lab, just clear. So, every table has 4 spectroscopes. So we start with about 4 to 6 people per table. But you'll notice I have different colored bulbs. You see the yellow one, we have some white bulbs, we have a black light bulb, we have a green one and a red one, and so forth. So we will have to share the bulbs, so I'm going to put the lights down, we'll cut these lights on, and these will be our sources of light. 2 more things though. The white bulbs, which are actually on that side of the lab, those will be kind of considered our incandescent bulbs, because I don't have any other incandescent bulbs. Okay? So the white bulbs are incandescents. You've heard of that term, right? An incandescent bulb. When you start having the new home stuff, you can replace bulbs, you make sure you find the right bulbs, okay? These are just the colored light bulbs, the advanced colors. And then the mercury source is the fluorescent bulb above us. Mercury, what's the symbol for mercury? Hg. Okay, so mercury, that's why you can't dispose of these mercury bulbs in the trash can, because they're made of mercury vapor. Do you think how healthy do you think that is to inhale? Not good, right? So mercury is pretty toxic, so we can't put those in the trash can. We dispose of mercury bulbs very specifically. So when it calls that specific bulb, find the specific bulb. Got it? Groups are 4 to 6. Come on back. Alright, so I have to give you some. It's just a thing. I gotta do it, but let's get to a rotation.
Where are you going?
Alright guys, there's nobody here. You have about 30 seconds to make a choice in life. You can't do yourself, I can't trust you much more than that. You have between 4 and 6 people at a big old lab station. Alright, so some of you guys, leave 4 people there. You got 4 people here, you got 4 people, 4 people. 5, you're good. I mean, when do you guys go to a really working journey? Okay. Just because I have smaller, I can have smaller groups, which usually like this. You guys do. Alright, so the instructions are on the lab sheet. So if you do not write on my lab sheets, you need to go ahead and go in order using the spectroscopes that are there. I have one on mine. Yeah, sorry, bring it. If there are any more, can you bring this back to try to Alright, you guys. Bring it. Okay.
me my purpose word for word. If I would want to do that, I would print this lab for you. But right now, all you need to do is come up with your own purpose for the lab. What's the purpose of the lab? Okay, so to observe and understand emissions measurement. That's one good way to say it. Alright, you guys need to get started. I'm going to put the lights off, turn on your lamp sources so that we can begin. I'm going to call out a couple more instructions, so when I say be quiet, you need to be quiet. Now, just because there are 6 people at your lab station, does not mean that you are 6. I would choose one person to work closely with, and then you can kind of shoot questions at other folks. Choose one person to work closely with, and then you shoot questions to other folks. Find the white bulb. Get going. Find the white bulb and follow the instructions on the paper.
Oh my God.
All right, guys, I'm gonna help you out. Eyes up here in 5, 4, 3, 2, 1. Eyes up here. If I can see your eyes, turn around. All right, so give me a thumbs up who's already seen the orange band and you saw it sitting on top of a 6 area. Okay, you have to make sure the light's coming into the spectroscope, it's reflected off a diffraction grating, and then the rainbow sits on top of the ruler. All right, so let's go. Bryce, what did you guys read?
6.2.
Okay, so 6.2 was the orange band. Everybody look at the top of the pre-lab paper. And what I'm sorry, where it says numbers, the numbers on the spectroscope scale represent what? 1,000 angstroms, right? So it gives you an example. It says 5.2 is not 5.2, it's what? Okay, so this 6.2 orange is not 6.2, it's what? Angstroms, right? A little knot. All right, so that's your measurement of the orange band in angstroms, and you guys now have the conversion on how to get this to meters. You just have to look in your notes or look in the lab. Okay, continue.
No, I mean, you clearly do 16. I know, I would do the same thing. I just went in there and inserted into zero. You get it for the new one. We're actually using it as a, so that would be 6.2. No, so that would actually be 6.2 times 10 to the negative 7. That's how many. All right. Light doesn't smell funny. I smell it. They do that though. Yeah. Right, never mind. I got everybody. Yeah, not her. Yeah, that's it. Yeah, so 4.8. Times 10 to the negative. Times 10 to the 14. Per second. And divide the energy. So it's 6.626 times 10 to the power of.
Alright, keep working, I'm just gonna tell you the next step, okay? Listen up, 3, 2, 1. You will continue calculating, you'll be moving on to colored bulbs and so forth. So, but at the number 3, you actually have to look at, number 4, you actually have to look at a specific gas. And I have hydrogen gas, I'm going to electrocute it. But I can only let a couple people see at a time because it's a tiny little valve of gas. So they only got 4 or 5 people who come out at the time. So when I say, okay, send me a group member, send me one person, and they're going to come back with information for the group, okay? So just as we go, I can wait a couple of times. All right, so send me a group member. Let's go just this half the lab. Guys, send a group. You guys hold on. Okay,
Should we do hours and then another color? Which one is she doing right now? It's what do we get?
And then there was like purple and that 4.5 dark purple.
Alright, next, If you do not want to see more, yes, please remember.
That's seven.
Like the South Lab, you guys haven't seen one
Oh, yeah, I just did. It's, 3.2 times. Six point six two six. And to the negative 26. No, it's 34. It's 34. So like that. Incorrect. 58. Usually 6.2. Alright, so it's about 3.2 times 10 to the negative 9. That's our energy. Or not the energy, that's our frequency.
Remember what we saw, 4-inch colors greater than length.
If you times it by 4.8 times 10 to the power for the energy, 3.2 is 10 to the negative 19. I do not. Alright, so let's do hours and one others. No, not
And do me a favor, do not move, hold on. If you grabbed a stool from another place, move it back and push your stools under. You guys are leaving the stools everywhere. There should be 4 stools per table. No more. It's okay if it's less. 4 stools per table. Alright, you guys are fine to leave the lamps on, TJ, you guys are fine to leave the lamps here. I gotta use some class. Alright, before you get diving deep into something else, hold up. Eyes up here for me so I can finish with class for today because I'll turn on announcements in a minute, okay? Alright, go back to my website because I know you guys were already there. Go to my website. Alright, put your Unit 1 test down for me. That's what we're reviewing during intervention. We'll have plenty of time. Just follow along with me now. Thank you. Alright, I'm going to ask for this one more time. Put your Unit 1 test down. Where are you supposed to be?
Your website.
Where at specifically on my website do you think? Problem set 5, okay, so that's just going to give me a chance to show you what problem set 5 looks like and then to see what I'm expecting for tonight so that if you have some questions you can ask me now. Alright, Elizabeth, please go to my website, go to problem set 5. Alright, when I'm asking for instructions, it's not optional. I'm just trying to make sure that we're all clear and we're on the same page. I'll have you for another 35 minutes in intervention, so hold off, okay? So, it looks like you guys, from my picking up on what you're putting down, it looks like you guys are doing okay with light. I can kill you on light on this problem set, but I'm going to try to start small. So what I'm looking for homework is the 5 questions under the, on problem set 5. You guys have this pulled up, right? Past the multiple choice or the true, false, and the matching. You see there's 10 questions of light. And then after that, there's more questions on light, but let's start small, okay? So I want you to do 1, 2, 6, 7, and 10. You're writing this down because I'm giving a special opportunity here. I'm going to keep my homework as it is. It's the problem set 5. You're doing questions 1, 2, 6, 7, and 10. Turn and talk to the person next to you on how you would approach 1. All right, give me what equation would be appropriate for number 1. What equation would we use for number 1? There's only 2 equations we've been working with. Well, explain it to me.
That's perfect, right. And then question 7. Look at question 7. Ariane, how would you approach question 7? What equation? This one has nothing to do with speed of light, actually. Look back at number 7. You're looking for energy, and you have frequency. Very good. Okay, so that's it. You're identifying your equation, you're plugging in, just make sure all your units are matching up. Question 10, since you just did the spectroscope lab, it should be fresh. Look at question 10. All right, so we have a way of measurement in the spectroscope. We know it doesn't mean anything. 3.5 means nothing to us. So we want to convert that to what? Angstrom, so the A, okay. What does the 3.5 mean in the spectroscope in angstroms? 3,500 angstroms, and then from there you can convert. And then we can go along whatever you need to do to get energy. All right, so we're going to how to approach. So I left it at problem set 5, the EMS stuff, because you can, I will ask you to do that. You see the table after this? There's a big table. Okay, I don't have it pulled up, I'm sorry. So on the big table, do you see the N equals thing? N equals, do you see that? So there's a diagram, which I'll pass, oops, where'd it go? It's back this way. A diagram, which looks like this, which is the Bohr model. Okay, so you don't actually need the entire Bohr model, but do you see the last column in the table? It says like it's energy released or absorbed. Well, you should be able to determine if energy is released or absorbed if it tells you how the electron's moving. So for example, if it's moving from N equals 2 to N equals 6, is energy released or absorbed in that transition? Absorbed because it's jumping, right? But if it was going from 6 to 2, it would be releasing. So that's kind of what we spoke of yesterday. Okay, so hopefully you're good on your homework, good? And you can continue making progress on your mini projects. All right, so I will turn on announcements in just a second. We are going to go over our Unit 1 test in intervention. So I've already handed you back the free response. I'm going to hand back the multiple choice. You can use your computers to work on homework for just a little bit, but we really won't need our computers at all for the Unit 1 review. Okay? So just keep looking at what you're looking at. I'm going to turn on announcements for you guys now, and I'm going to pass out multiple choice. I will require you to leave my room, though, for intervention, like to get a break before intervention starts. Bathroom and such.
Yeah.